Today's lesson is 5.6, Rates of Change in Rational Functions. So one of the big expectations of this course is that you are able to find rates of change. That's why we keep coming back to this topic all year. So we're still talking about everything that you know about rates of change. We're just going to apply it this time to rational functions. So looking at this picture here, we want to fill in the blanks. IROC, remember that means instantaneous rate of change at a vertical asymptote. So what is the instantaneous rate of change at a vertical asymptote or at a hole? What is the instantaneous rate of change? If I could draw an asymptote here, or draw an asymptote at the hole, what would we get? What's the instantaneous rate of change? It's undefined. So this is where we have discontinuities, we have an undefined rate of change. What about near a vertical asymptote? So near this asymptote, that means where my function is approaching it, getting really, really close. Right near, what do you think, what kind of slope would we see here? And what kind of slope would we see here? We're getting very large numbers, positive infinity or negative infinity, very steep. To draw a line here, we have to be almost completely steep. So we're getting our instantaneous rate of change, which is the slope of the tangent line at that point, will be very large. What about near a horizontal asymptote? So we have a horizontal asymptote here. Instantaneous rates of change near the horizontal asymptote. It depends where you are, but near it is like this. Over here, my graph is not really near my horizontal asymptote there. My graph is near the horizontal asymptote here. So what's the rate of change of my function, the red line right here? So here we're approaching slopes of 0 for our tangent lines. If we could draw them in here, they would be pretty straight right there. So we have almost 0 rates of change. In your textbook, I just copied out this example here. It's about connecting the instantaneous rate of change to the slope of a tangent. We talked about this before. So to estimate the slope of the tangent, so we've got this graph here. We want to figure out what the slope of the tangent line is when x equals -5. Now we don't have to graph it to figure out what the graph would look like and then draw a tangent line. We don't want to do that. That's kind of our worst case scenario, drawing in a tangent line. We want to calculate it. The way the textbook does this question, the way they solve it, is they're using the difference quotient here, let h equals 0.001, subbing into the difference quotient. So so the a value, remember the a value is whatever is kind of the point of interest here, the x value that we are looking for our point of tangency. So that goes in for this. You can also, I said this in other videos, you can, instead of an a, you can make those x's if you want. Sometimes students prefer to just leave it an x instead of bringing in the a, but in this case, we just switch it directly to a -5, then h is 0.01. Use the difference quotient. We sub it all into this f, so f at -4.99 we put up here, wherever there's x is -4.99, work it all out, and we've got approximately 0.7504, so they're at rounding that there. So this is our instantaneous, this is an average rate of change as close as we can get to the slope of the tangent just by subbing in a number close to 0. The solution here uses this value for a difference quotient, so that's why we're having estimation, because we're not having a h value of 0. We're very, very close to 0, but we can't sub in a 0 there. We're going to find the instantaneous rate of change by manipulating the difference quotient algebraically. So the method we're going to do now is the preferred method. It's the better method. There's none of this rounding and a whole bunch of 9s and decimals and zeros. So we're going to try and do this a little more cleaner here. So here's the same function. We're going to algebraically manipulate by substituting into the difference quotient here. So I'm going to first start by writing here on the side that you can let a equal x if you want to. Let a equal x to change it. So I have average rate of change here equals f at x plus h minus f at x all over h. Now you could also sub in here, and we're not going to do this, but you you could sub in x equals -5 here. We're not going to do that. I'm going to do it kind of the more complicated way, and I'll explain that in a minute, but you could certainly right here put -5s in all for those x's or for those a's. You could do that right now. But we're just going to leave everything as variables for now. It's a little more complicated to work through, but sometimes it has a benefit at the end on the specific questions, and I'll get into that in a minute. So back to what I was talking about here. Now, looking at just a review, we've done lots of this. F at x plus h. That means everywhere I had an x, I'm going to replace it with an x plus h. So this x is going to become x plus h, and the denominator x is x plus h. So I'll keep it in green just to help you see it here. F at x plus h, what I circled in green here, that is now x plus h over x plus h plus 3. Then I will put the other part, I'm going to circle here, minus f at x. So this is, erase all this stuff here. This is f at x in the top left. That's my f at x. So I'm going to just rewrite this whole thing and put it in for f at x. Minus, that minus sign's important. F at x is x over x plus 3. And then the denominator, it's all over h. And this is our average rate of change, what we've got here. Okay, now when I look at the colored numerator pieces here, the green and the blue, I need a common denominator so that I can subtract them from each other. The common denominator is not, people often think, oh, look, that's x plus h plus 3, and that's x plus 3. They're almost the same. Let's just use x plus h plus 3 and just add an h on here to make a common denominator. That's not how it works. So I'm just going to do an aside here on the left to show you why you can't do it that way. Always change it into numbers. When you don't understand or you think you know what to do is right or wrong, just try it with numbers. So let's just say we had 1 over, instead of x plus h plus 3, say we had 3 plus 4 plus 5. This is an aside, okay? This is just to help you understand the common denominator issue that a lot of students have. Instead of x plus h plus 3, we're doing 3 plus 4 plus 5, and x plus 3, let's say that's 3 plus 4, okay? So this is really 1 over 12 minus 1 over 7. The common denominator, to get the common denominator here, we would be doing 12 times 7 to get a common denominator. We would not just add on, 5 here to get a common denominator. That would be wrong. Okay, so these, we can't just put these denominators here together and say, well, I'm just going to use this one because this one is common. This is adding. When you're adding numbers, you can't jump to a common denominator. I'll give you one other explanation of that. If I had 1 over 1 plus 3 and I had to add 1 over 1 plus 4, well, I can't make the common denominator here a 5 just because this is a bigger one. You have to first simplify your denominators and then multiply them together. Okay, so let's go back over. I hope that helps explain what I'm doing here. So I'm going to put my equal sign and actually see this being divided by h. Instead of that divided by h, instead of me putting that, I'm going to move it over to the right, to the far right, and I'm going to put divided by h over here. Because I have too many levels of fractions and we're not allowed to have that. So I'm going to have kind of a big square bracket here with all my other stuff inside, but I'm not going to keep the divided by h because it's too many levels. Okay, so we conclude our common denominator is x plus h plus 3, x plus h plus 3 times x plus 3. That's the common denominator. So the numerator for the first one was already x plus h, but now I have to bring in the extra piece. I'm going to put brackets on it. Now I have to bring in my extra denominator. What you multiply by the bottom, you must multiply by the top as well. So I have to do that. Minus, and we do it all again for the other side. So on the other side, we've got over x plus h plus 3 and then the blue one is x plus 3. So there's our common denominator. We already had an x in the numerator. So what we need to introduce, what's missing is the green part, the x plus h plus 3. Okay, now we have one big common denominator. I'm not going to do the colors anymore. One big common denominator, which is x plus h plus 3 times x plus 3. That's our common denominator. We're going to simplify our numerators now. So a little bit of binomial expansion here. X times x squared. X times 3, x times 3 is 3x. H times x, you can either write hx or xh. Usually we go with alphabetical order, but it's not really a big deal. So we'll put hx, and h times 3 is 3h. Now be careful of this minus sign. I have to multiply the negative in as well as multiply the x in. So I'm going to do those two things at once. So it's negative x squared, and then the whole thing gets multiplied here. So negative x times h is negative hx. I'm running out of operation line here. And negative x times 3, don't forget the negative, is negative 3x, and it's all divided by h. Instead of writing divided by h, I'm going to write it multiply 1 over h. Same thing. Okay, look at that numerator there. What can we do? Well, the x squareds. Look at the x squareds. They will cancel out. Anything else? The hx cancel out. Anything else? Yes, I can hear you saying it, of course. The 3x's cancel out. What do we got here? What's left? This is it. That's all that's left in the numerator. Awesome. Okay, so that's 3h over our denominator of x plus h plus 3 times x plus 3 times 1 over h. So this will always happen when you're algebraically manipulating. You'll get a lot of things canceling out. We can cancel out again here the h's. The h with the 3h cancels with this h in the denominator. It's a monomial. They're both monomials. We can cancel them both out. I'm just going to pause this so I can erase all this stuff that I wrote over here on this side. I'm just going to erase all of that. Okay, what have we got? We've got the average rate of, so I'm moving it all up to the top left now. The average rate of change is equal to, we have a numerator of 3, and in our denominator, this is our good old denominator. We've been carrying this around since the beginning of the question almost. X plus 3. Okay, so I'm going to put an arrow here to indicate where I went. So when you're just looking at a handwritten page, I need to be able to follow what you're doing here. So what next? Do you remember the next step here? This is an average rate of change. Well, we would like an instantaneous rate of change. I would like this to be instantaneous rate of change. For an instantaneous rate of change, we don't want h to be something like 0.01, because then that means we're looking at some point on a graph. Let's say we're like this here, and maybe x is 2. So here's when x is 2, and I'm going right beside when x is 2, 2.001, right beside when x is 2, and then I'm finding the slope between those 2 points. That's not what I want. That's an average rate of change. I want an instantaneous rate of change. I just want to know what the slope is just at 2. That I can achieve that when h equals 0. So I want h to equal 0, not 0.01. So I'm going to do that. I can do that now. Let h equal 0, because I don't have this over here back to the left. I don't have this divided by h, my denominator of 0 anymore. I kind of faked my way around that, right? So that's not there, so I don't have to worry about subbing in a denominator of 0. When I sub in h equals 0, I then am looking for the instantaneous rate of change. And actually, it's really more correct to write it like, let me change that, and write it as h approaches 0. As h approaches 0, and we're going to sub it in 0, As h approaches 0, we're going to find the instantaneous rate of change. So to do that, we're going to sub in h equals 0. Our numerator is still 3. On our denominator, we'll put in zeros. So here we'll just have x plus 0 plus 3. So I'm just going to put x plus 3. Again, x plus 3 is what we have. And I don't need to, but I'm just going to put those denominators together as x plus 3 squared. So what we have here is a little kind of formula for finding the slope of any tangent line anywhere on this function. That's why I didn't sub in x equals -5 right away. Because if the question goes on to have a part B that says, okay, what about when the slope, what's the slope of the tangent line when x equals 12? Well, now I can just sub a 12 in there. What about when x equals -8? Well, now I can just sub in a -8 in here, or I can sub in a -5 here. So if there's multi-parts to the question, it's better to just keep the variables, simplify it once. Otherwise, you would have to do the question over and over again. If you subbed in a -5 here and a -5 here, or sorry, yeah, well here, everywhere we had -5s, it would be faster to get all this done. But if there's a part B to the question that asks for another spot on the graph, then you're going to have to do it all again. So just look at the question. It's definitely faster, cleaner to do it this way. So if you can, then do it that way. But if not, now you can see how to do it the other way. So what we're going to do is our very last step. Now we're going to sub in our value. The question asked for when x equals -5. That's what the question was originally asking. So I can now find the instantaneous rate of change by subbing in a -5 in for x. And that's going to give me -5 plus 3, right? That's going to be -2. Squared is 4. And if you remember what the textbook had, they had an approximate 0.75, I can't remember what the rest of it was, 0.7504. So that's what the textbook had, and they had a little dot above it, 0.7504, I think is what it was, because they subbed in h equals 0. I think that's what they used. But we are better here. Our answer is way better than this. This is an exact answer here. This is exactly what the slope of the tangent line is when x equals -5. If we had a graph, I'm not going to graph the rational function, but when x is -5 right here, I know that the slope of the tangent line of that function when x is -5 is exactly 0.75 or 3/4. So we have the exact answer there, and that's the instantaneous rate of change. There's no approximation symbol on it. That's exactly what it is. So that's your algebraic manipulation. This is the last slide. This is all in your handout if you have the handout. Try solving your homework questions with a variety of ways. So the way that I just showed you is algebraic manipulation, but you might also want to review just using the difference quotient, subbing in a small value for h. Just to review rates of change, you've got all of our chapter 2 was rates of change, so you've got all kinds of notes on rates of change. Now's a good time to review all those. Bunch of text corrections, lovely, and some homework tips, and also if you're doing chapter reviews, so you can read through this stuff as you get there. That's the end of today's lesson.